Good morning, everybody. I'd like to thank you all for attending our Forging Ahead with the AFRC at NMIS, an introduction to forging and incremental technologies webinar. Before we move on, I've just got to do a little bit of housekeeping. Give me a second. There we go. First of all, this webinar has been recorded and it will be made available on our YouTube channel, so please feel free to share it. Please ensure your microphones and webcams are turned off during the session to avoid any background noise. You can type your questions via the chat tool. We will allocate time at the end of everybody's presentations to answer those questions. Also, please use the hashtag NMIS Insights for any questions on Twitter at NMIS_group. And please take some time to complete our survey at the end of the webinar. So agenda for today, firstly, we'll quickly go through what the National Manufacturing Institute Scotland is, and that's with myself. We'll then move on to Forging Ahead with Mark O'Hare, then on to Forging Modelling with Dr. Javid Falsafi. After that, we'll cover incremental forming of metals with May Tuckwood, and then on to working with NMIS with Jared Brown. After those presentations, then we'll have the questions and answer session. So what is National Manufacturing Institute for Scotland? Well, NMIS is a group of industry-led manufacturing, research and development facilities where industry, academia and government work together to transform skills, productivity and innovation, to attract investment and make Scotland and the UK a global leader in advanced manufacturing. So what will NMIS do? Well, we'll increase productivity by reducing barriers to innovation, some of which we'll discuss today. We'll stimulate investment and make Scottish manufacturing more competitive. We'll stimulate job creation, improve supply chain links. We'll inspire and attract talent by giving workforces and businesses the skills they need. And we'll support businesses of all sizes in multiple sectors across the whole of Scotland and the UK. So NMIS is operated by the University of Strathclyde and it's supported by the Scottish Government, Scottish Enterprise, Highland and Islands Enterprise, the High Value Manufacturing Catapult, Skills Development Scotland, Renfrewshire Council, the Scottish Funding Council. It's also supported by universities across the length and breadth of Scotland, and it really is a countrywide initiative. So how is NMIS made up? Well, we have our specialist centres, the AFRC and LMC. We have our new Manufacturing Skills Academy, providing professional development courses. In the future, we'll have our digital factory and collaboration hub. The AFRC itself is a globally recognised centre for metal forming and forging research and development, and we'll discuss part of that today. And importantly, NMIS is operating right now, so you can engage with us immediately. So Forging Incremental Technology team, that sits within the AFRC. The AFRC itself has invested over 10 million in forging and incremental technologies, developed robust capabilities in process development and optimization, works directly with industry and academia to demonstrate benefits of processes, addressing the fundamentals of deformation, behaviour, prediction and control, providing a unique range of solutions for industry. So thanks for listening. I'll now pass you over to my colleague Mark O'Hare to go through Forging Ahead at the AFRC.
Thanks very much, David. So yeah, my role today is covering across the forging technologies that that you'll see in the centre. Whether you've been there or whether you're looking forward to a trip anytime soon, as soon as we can open the building again. 1 second. So forging at the FRC, for those of you who know the forging team or the Forging Incremental Technologies team, forging has been a core technology since the beginning of the AFRC. The team itself sits with around 20 engineers across the various disciplines that you'll see today, represented by my colleagues. Ultimately, forging at the heart of the FRC, we recognise the fact that the forging industry in the UK manufacturing supply chain is a key area that needs to develop and needs to support OEMs, tier ones, etc., these kind of things. But also at the same time, the drive for cost reduction, it becomes really clear that all of those cost reductions commonly get pushed right down the supply chain, and the forging supply chain is the one that suffers, or one of those that suffers at the bottom end of that, where they have little time or little investment to support innovation and their own development as well. It's not through any fault of their own, but it's just through that constant drive for cost reduction. So the university recognised this in the FRC and supported this with the idea of creating a facility that gives companies the opportunity to develop their own technologies offline from production. We look at the fundamentals of deformation and materials evolution and link that base research that we get at the kind of traditional university end, link it with production scale demonstration. So we do the demonstration and the validation and the development of your ideas, your technologies, but we can do them without disturbing your production capabilities. Innovation in general, it's always been at the heart of the forging team's capability. With a particular good example of it is one of our very first machines we brought into the FRC, going back some way now. We looked at working with one of the major press suppliers and developing their capability for servo-based driven technology. This was linked directly with the ability to forge difficult to forge alloys with narrow process windows and strict performance characteristics. In order to forge those alloys, you need much greater control, much greater capability. So the servo controls that we brought in and worked with the partner on this gave us that real precise control over the forging windows and the characterization of the forming processes on site at the FRC, validating that technology for the supply chain and proving that out. And we've now seen that supplier go on to sell those presses with the servo-based technology into the supply chain. So it was a really good process that came out with the practical outcomes of having a validated new technology introduced into the supply chain, albeit press manufacturing rather than the actual forging supply chain. But it offers companies like yourselves the capabilities of press manufacture using servo technology to control your processes. And I'll come back to that a little bit more on as we move into the future of forging. Where do we feel we're heading in that direction? Forging at the FRC, basically, technology innovation is a complex relationship with business and technical demands. And you'll see a wonderful little graphic on the right-hand side. Innovation doesn't just come from a good idea. There's got to be a route to market. There's got to be fundamentals development, whether that be research or whether that be control of new IP, these kind of things that have got to come together. But it's all got to come together in this wonderful alignment of ideas, route to market, IP control, funding as well. How can we leverage UK funding competitions to help your innovation and your demands? But in order to that, we need to satisfy the likes of, does it have legitimate research? Does it have legitimate use in the supply chain, as well as somebody actually asking for this? And that's where we see this complex relationship. But the benefits come from that in real precise innovation. And you can see on our slide here, likes of high accuracy and control, reduced processing times, and we reduce the amount of stock with near net shape and precision forging as we get to the better end of forging and control. And equally, can we move into the digital age? And I know we've got a number of partners on today that are looking around simulation capabilities and where we want to go in that direction as well. How we do that, we need to break that down into various problems that we can solve and support the supply chain with. By delivering innovation out into the supply chain allows you to characterize parts, allows you to characterize and optimize your processes and the parameters that go with them. Perfect example being a Catapult program that we're running at the moment. Catapult programs are our internal funded programs that help us distribute research out to the industry, and my colleague Gerard Brown will come to that later on. We're looking at the idea of how do we manage, how do we improve die wear through thermal contact. during the forging process. Sorry. What we're trying to do with that is look at an innovative method for developing near-surface temperature monitoring with live data streams. And that gives us the opportunity to use temperature monitoring to understand if there's going to be a breakdown in the die surface or any die surface coatings, for example. But equally, it gives us different opportunities in how we deploy that technology going forward. Can we use that technology to understand if there's any underfilling components, for example, by baselining a temperature profile across a certain feature, for example? Gives us lots of opportunities, and using these sensing technologies allows us to capture the data going forward, and in kind of true big data form, you can then analyze that and take that into whether it be performance or optimization of parameters, or whether it be into your predictive software and going forward. Gives us lots of opportunities, and that's a particular focus area of the AFRC. When we take that in terms of the general message across from that, the AFRC, we're committed to delivering innovation across the supply chain, but equally, as an institution, we have our own themes, our own values that we work to. And the university's values really represent how we plan to deliver this capability into the supply chain itself. We are people orientated, and you'll see when we carry that across into our themes, there's particular focus going to be on skills and training going forward, for example. Bold and innovative, as I've covered already. Collaborative is a key area of the FRC. We work hand in hand with you as suppliers and the supply chain as a whole as well. And ambitious, out there research, let's try and bring out the innovative ideas that the UK is famous for creating and bring that into the supply chain. There are various goals. We have challenges as the FRC and the university, and we really challenge ourselves and our engineers to deliver these going forward. In terms of the various themes, we align these in particular to visions and trends. Electrification, for example, being the key area. It's the buzzword at the moment, but ultimately that's where all the funding competitions are supporting their technologies going forward. So not only are we focused on delivering key innovative ideas around that, but also how do we turn your ideas and leverage that into those particular areas. So for example, you may be forging a component for the aerospace industry at the moment, but can you deploy that technology, that process into an electrification application as well, and kind of further spread your ideas. Supply chain analysis and development. Simple, how do we take all of this technology and deploy it into the supply chain? How do we bring it to you? And how do we solve, kind of hand in hand, solve some of the problems that you see, whether it be die life, whether it be cracking in parts, all of these kind of things that you'll see on your day-to-day lines. And then we get into the real innovation ideas. Die life improvement. I've already covered the idea of how do we monitor die life, or how do we improve die life through thermal measurement. But the likes of new technologies of additive components, etc., moving forward, rather than just cut a new die or flood weld, etc., can we use additive technologies to repair dies and extend the life, thus supporting the cost-cutting measures. Smart forging, digital twins, etc. Ultimately, where we would like to go is the fact that we don't want to see excessive prototyping, excessive testing. We want to be able to design our processes within visualization and simulation softwares, but have those fully representative and fully supported and validated. Those are a particular example of where we need to bring in the likes of the sensor technologies. In order to have those accurate, we need to understand and capture what's going on at the moment. So that's directly linked to the sensor technologies that I've just mentioned. Everyone likes materials properties enhancement. They want to get more from their parts or more from their dies. Can we work with heat treatment suppliers? How do we support that going forward to get the best out of the materials, or validate the digital element of new materials coming on board? Following that up, a key area that we need to investigate as a supply chain, both in the research end and in the production end, is how do we validate future changes going forward? Our validation shouldn't just be a case of we've brought this new process in, it's costing us all of these, it's saving all of these costs, but we still have to jump through all the same old hoops in order to get the part validated. can we instrument and engage the validation standards committees to accept new technologies through different capabilities of validation? For example, could we use the digital technologies that we have to do digital validation rather than do all of your same old tensile tests? Could we just do a virtual simulation of a tensile test drawn directly from a part? These are all things that are long-term goals, but how do we support that? In terms of long-term goals, we are aware that skills and training, the sector itself, are heading towards skills and training gap, and how do we support that technology? The AFRC at NMIS, we're supporting that with the likes of our Manufacturing Skills Academy, and we're working directly with them to try and develop capabilities and training courses to support you as a supply chain, but also not just support and bring your new employees or new graduates, new apprentices in, but also how do we bring them up to the level where they're doing the direct R&D that's appropriate to new research and to new funding competitions, and they're aware of how to deliver that, and ultimately get to the goal of that year on year up to date, rather than having to go away and do a literature review for every new employee that comes in, for example. How do we deliver that at the AFRC? Well, currently we have a large range of equipment that goes across the centre, various heating technologies, test technologies, etc., that give us that capability. I've already mentioned our 500-ton servo drive upsetter. As I mentioned, it gives new technology or new technology for that supplier, give variable control over velocity, strain rates, etc. But equally, we can deploy all those technologies and all the sensor technologies, etc., that we're bringing across all of our various bits of equipment. There's particular focus on the various heating technologies at the moment. How do we manage that? These are the heating technologies around how we support our forging presses, but equally we have supporting technologies for some of the forming capability that you hear about over this afternoon, or over this morning, sorry. More focused, how do we deliver that going forward? The vision and trends, we take all of our key directives from the likes of the trends from Advanced Propulsion Centre, ATI, etc. Where is market heading for UK manufacturing? Supply chain development, as I mentioned, how do we look at the core technologies that are deployed out to the supply chain? We don't want to be sitting here with a fancy new workshop basically saying you need to buy this as a supplier. What we're actually saying is each one of our pieces of the kit is a demonstrator to you, and we'll have supporting technologies like the sensors that go forward with that. The perfect example for that is going to be the press that you can see in the middle, where we are delivering a 2,000-ton open die and closed die and isothermal currently over the next kind of 12 to 18 months as it comes online. It's currently being installed at the AFRC, but it's not about having this fancy new shiny bit of kit. It's actually about being the online demonstrator that allows you as a supply chain to see how we're deploying research onto presses and give you that capability going forward. A perfect example of that is actually if we jump down to our smart forging. We have a fantastic partnership with Beckhoff on our 500-ton hydraulic press. The 500-ton hydraulic press is one of our original bits of equipment that came into the centre early on, but we're looking at live data instrumentation on that press so we can monitor it offline and we can look at the live data as it comes through the forging cycle. Why is that important? We take that into the simulation and the visualization methodologies that we're bringing from FutureForge, with the idea that we can predict the forging process, but equally we can use the visualization technologies to train new operators, for example, in an offline visualization suite. And equally, that's something we could do going forward for the likes of other presses that we can capture data from. Skills and training, I've already mentioned, for example, we are moving forward with the idea of this Manufacturing Skills Academy. And equally, working with David and myself, for example, we are bringing in training courses for forging. We're particularly focused in this area to try and address the skills gap that's heading that way. Validation. As I mentioned already, how do we use the traditional methodologies, the likes of the tensile testing, your metrology, your standards committees, to validate current components, but equally use the digital element of that to capture and validate digitally and merge those two areas of focus going forward. So we very much see the future of forging being at the AFRC with the capability based around our future forge technology, the 2,000-ton press. But as I mentioned, at the heart of it, it's not the press, it's the innovation that goes with it and how we help the supply chain deliver innovation, not how we simply deliver and preach innovation out to the supply chain. We're here, we are working together, and we're here to support your technologies going forward. So that's what I really wanted to cover going for forging and taking that forward. If there are any questions, obviously please add them to the question and answers for later on. Thank you very much, and I'll pass back to David.
Thanks, Mark. Interesting presentation there. And if I can just reiterate what Mark said there, if you have any questions, please use the question and answers chat box. I'll now pass you over to my colleague, Javed Falsafi, for forging modeling.
So, hello everyone. Building up on what Mark just presented, I'm going to focus on modeling for forging processes today. So look at what are the rational process design steps for forging in general, and where the process modeling sits in the chain of the steps. Then the main objectives of forging process modeling. After that, an overview of the workflow to create an effective process simulation and what goes into it. And at the end, I'll wrap up with a case study. First up is how we actually design for the forging process. What steps do we take? This is actually a breakdown of steps or work packages. Things start with a blank sheet of paper using experience-based knowledge to work at the preliminary die design and selection of process parameters. Then the initial design and process conditions will be then verified using process modeling instead of two. Based on the result of the simulation, die design and the process variables are then updated. Sometimes the last two steps gets repeated quite a few times until a satisfactory design is achieved. Then we complete the die design and manufacture the dies to conduct forging trials on production equipment. Again, if necessary, the results of this stage are fed back to the modeling to eventually be finalizing the design and the process conditions, so we achieve a quality part and a viable process at the end. We can see that the process modeling is an important step in the forging process design, and it gets revisited several times. It has a high potential to reduce process design lead time and associated costs. Actually, using finite element process simulation in forging has been around for 5 decades now. However, it took a while before the advancements of remeshing methods and computational technology makes the industrial application of finite element simulation practical for the industry. Now we see these days computer modeling have gained wide acceptance in the industry and become an integral part of the forging design, with the goal of rapid development of right the first time process, also enhancing the performance of the components through better understanding of the process and the controls. So in terms of some of the main objectives of the process simulation, I've listed some in this slide and categorized in 3 categories. First is adequate die design and establishing process parameters, which is about design of the forging sequence, the preform shape, prediction and improvement of flash dimensions and material yield, prediction and elimination of defects, faults, or fractures, and also investigating the effect of temperature and friction on metal flow. Second, in a more advanced level, improving part quality and complexity through prediction of microstructural features, prediction of elastic recovery, residual stress that could potentially lead to part distortion and tolerance nonconformity. And last but not least, we've got prediction of forging load and energy, as well as tool stresses and tool life. Next, I'm going to take you through an overview of the workflow to develop a reliable and effective process model. We can see in this workflow regarding the inputs, so we've got the material parameters for the workpiece and die. They should be properly specified. The geometry of the toolset and workpiece. Sometimes the simulation can be 2D axisymmetric or 3D depending on the details of the geometry. In terms of process parameters, all the temperatures, contact conditions, all the timings, transfer time, rest time, and very importantly, press type and all the associated parameters that goes with that specific press type should be properly specified. And then in the process simulation, in the middle, is where the magic of fine element happens, basically. And we can preview the metal flow, the die filling, the state variables throughout the forging, all the potential defects, loads, and stresses. And integrated with this simulation, we can have microstructure modeling to preview metallurgical features as well. Eventually, with a verified model, we can improve the design iteratively, and we can finally achieve an optimum process. Next, I've got a case study for you. I'm going to take you through that. It was about the forging car engine pistons from aluminum metal matrix composite. So this slide shows how the initial geometry was modified. You can see in the middle. Unforgeable features were removed and draft angles were added. And finally, the toolset was created out of that. We considered punch to be elastic so we can study the stresses and tool wear. Very important part of this was the material. The material was aluminum 2124 with 25% silicon carbide. And it was manufactured through powder metallurgy. This composite was modeled as rigid plastic, isotropic material, and we characterized the flow curves with compression tests at various temperatures, strain and strain rates. You can see some of the flow curves on the left-hand side, 2 temperatures at various strain rates. And next is actually some of the process parameters. So we were looking to compare 2 types of forging processes. The hydraulic press, which we considered that to be isothermal forging due to die chain that happens in the material. Also screw press, which is a fast-acting press. So we are not really concerned with the die chaining that much. So these 2 process types were something that we were trying to study. Here at the bottom, you can see a quick view of progression of material flow and the die filling through the skirt, bed, and the pinhole areas. Next, I've got an animation here from some of the state variables, and this was the case of a screw press. Let's have a quick look again. So you can see how the material deforms, and it starts to move upwards and fill all the die cavity, and finally it starts to flow out of the flash like a flat wire. So again, state variables at the end of the forging, and you can see also the load profile for the screw press and hydraulic press versus the stroke. Also the energy required for the process on the right-hand side. And one of the most important things which is different between the 2 cases is the strain rate. You can see that it's like something around 200, 300 times higher in case of a screw press. And that's because it's a fast-acting process, and the material flows very, very rapidly into the die cavity. In terms of some of the detailed studies we carried out a sensitivity analysis to analyze the impact of temperature on the tool wear. Here we've got a punch wear map at the left-hand side at various initial billet temperature. On the right-hand side, at the top, you can see the trend. The higher the flow velocity, along with the higher pressure in the screw press, has resulted in more tool wear. You can see that in the orange line. And then as we increase the forging temperature, tool wear starts to decrease. That's because the material flows easier. And also there are some other features associated with that, including the pressure, etc. Forging load also is shown here at various initial billet temperature, and the final range of the temperature is shown with that blue line across the part. So in case of the screw press, we can see that there is a significant amount of adiabatic heating across the part, and the range of temperature is very wide. So one of the things that was important for us was to avoid any melting. So because of that, we can see that 450 is quite a suitable temperature for the screw press, and obviously for the hydraulic press, it's fairly straightforward. Any of those temperatures would do. And in general, we can see that for the tool wear, in terms of hydraulic press, the highest temperature used for the screw press is almost the ballpark we have for the hydraulic press, regardless of the temperature. And at the end, what we were trying to look at was tool stress and other aspects of tool life. Low cycle fatigue is studied here. You can see the map of the stress across the punch for the screw press and hydraulic press, both at 450. What we are trying to always have is to have a predominant compressive stress across the parts, across the tool set, because that reduces the chance of any low cycle fatigue happening in the part. Even though there might be some areas, small areas experiencing positive and tensile stresses, we need to make sure that it is low enough. On the right-hand side, you can see that the node of frequency of maximum principal stress across the punch. And there is a tiny bit on the right-hand side, on the positive side, which are still lower than 200 megapascal, which is quite acceptable. And that was basically the study we carried out. So that's pretty much it in terms of my presentation and the case study. Thanks very much.
Thanks, Javed. I'll now pass you over to my colleague, May Tuckwood, to go over incremental forming of metals.
Thanks, David, and hello to everyone who's here. So I'm just going to give an overview of our incremental forming capabilities within AFRC at NMIS. So in our incremental forming processes that we have in-house at AFRC, we've got 5 primary technologies that we work within, and that's flow, shear and spin forming, rotary forging and radial forging. And these are near net shape technologies, and they're all rotational, so the types of components that we're considering are axisymmetric typically. Now, the adoption of these processes is cross-sectoral, so there's components from automotive and aerospace sectors traditionally, but also extending to the energy sector and oil and gas. So with that comes a range of different components, a range of different component scales, but also a range of material types. So some of the materials that we're targeting are steel alloys, nickel alloys, aluminiums, titaniums and coppers, but not limited to these. One of the other things that we have looked at within our team are development alloys, but also one of the key benefits of working with us at AFRC is that we have in-house and also in-team materials characterization and residual stress capabilities, which means that for the majority of our projects, we're actually starting front end. We're starting with understanding the raw material prior to the processing of the component. We extend that right through to the final part, so that's post-forming, but also in the final condition of supply, whether that's heat treated. And another thing we do look to understand is the effect of heat treatments and how that could impact the formability of the component. So starting off with flow and shear forming, and just to give you an overview of these technologies. So we've got 2 primary pieces of equipment within the AFRC. We've got a large horizontal flow former, an STR 600, which has 3 rollers and 50-ton capacity each. We've also got a smaller machine, our VUD 600, which has a lower load capacity at 30 tons per roller, but does give us greater variability in terms of the complexity of the components. So on the left here, you can see an example of flow forming. So if you're unfamiliar with flow forming, essentially we've got a forged and machined preform input. So we're starting with bulk material. We've got 3 large rollers here, each of which are offset to take their own individual portion of that starting thickness of material. Now what we're doing here is reducing the thickness and we've got axial displacement as those rollers move along the axis of the mandrel. So in terms of thicknesses, we're looking at reductions here between 20 and 80% of the original starting thickness, and elongation up to 200%. So conventionally, these types of components, shafts and parts like that, would be machined from solid. So the volume of material being lost is significant, sometimes 80 to 90% of the original starting material. So by forming this way, yes, we've got an element of machining in the first instance to create the preform, but the material utilisation is drastically improved. We can also create varying wall thicknesses, and this is really the types of components that this process is best suited for. Those types of features may be used for mounting other components within the assembly where you require higher thickness and higher strength in that region. But also often the formed surface is left as formed with no further machining required. So in terms of your manufacturing process as a whole, it's much leaner. We can start to reduce steps in that process. Shear forming is another process that we can conduct on the same machine. Now, both are similar to spinning, I should say. Each of these technologies are derived from conventional spinning, but one thing that we don't do is that in a manual sense, but embedding those traditional skills into a more controlled form to create complex components in a way where we can tightly control wall thickness and surface finish. So in shear forming, we're starting with plate or sheet material, typically in thicknesses ranging between 3 and 15 millimeters. We have gone as far as 20 in some steel alloys. And we're creating a conical form in shear forming, whereby we're reducing that thickness with respect to the angle that we're forming at. So typically ranging from somewhere around 18 or 20 degrees up to around 60-degree cone angles. Again, these types of components would conventionally be machined from solid, or they would be made from multiple parts where you've got the added effects of welding, heat effects of welding, and final preparation to get to the finished part. Now on the left here, you can see an example of our vertical machine. So this particular bit of equipment, we very often refer to this as our small flow former. Now it's small in footprint, however, it can do larger diameter range as compared to the horizontal machine, up to 800 millimeters. Now its vertical setup gives us much more flexibility. So we've got things like angled roller housings, which means we can form a contact point with the material at different angles, but we can also add things like features onto the parts. So external features is possible with driven rollers, but internal features also. So you can see some of the types of components on the bottom there, and things like hub components with splines and also pulleys are the types of parts that are targeted on this machine. It is also broadly used in the automotive industry for things like alloy wheels. So application prospects of these types of processes vary broadly. So moving on to our other technologies in our incremental forming, are rotary and radial forging. So similarly, we're creating near net shaped surfaces. I should mention our flow and shear forming are cold processes. You can see they're being cooled throughout. We're not adding any heat other than that and just by friction. Now in the rotary forging here, you can see that the part's lubricated, but it isn't cooled. So in this technology, similar to conventional forging, there is a lower die. However, the key differentiating factor here is that the upper die is conical. It's also nutating, and our machine's got a 45-degree nutation angle, which again gives us much more flexibility in terms of the component features that we can form. The key advantage of the conical tool is that the contact surface is drastically reduced. So approximately 30% of the workpiece is in contact at any one time, and as with the other technologies, it's continuously shifting, meaning that compared to your conventional forging routes, you're forming with much less force. So some of the example components on the bottom of the slide here, you can see some of those would be formed in a lower die cavity, but also in the video there, you can see us adding a flange feature onto a shaft type structure. Now the advantage there again is that we're eliminating the need for a weld. That's then been formed in a single component, and you're getting the added benefits of the incremental forming in terms of the microstructural properties of the part. Now, radial forging, that's the final process I'll discuss today, our SKK10 radial forge. So you can see the process there running. So there's 4 hammers that are acting simultaneously to incrementally form this part. Now this process is the one technology that we have in incremental forming, whereby it can be done cold, semi-hot or hot. But our machine at AFRC, it is in a cell, it is automated, and we've also got inline induction heating also for those hot processing. Now, the key advantage of radial forging, particularly compared to flow forming or some of our other cylindrical forming processes, is the ability to create internal features. So flow forming and shear forming are limited on that internal diameter being constant. The part is forming against the mandrel at all times. And while the same is true for radial forging, the mechanism of the process lends itself well to internal steps. So you can see in some of the examples there, and also internal splines, which is particularly advantageous for transmission shafts. Now, just to summarise some of the key benefits across these areas. Now, we look at these technologies in isolation. However, many of our projects, particularly over the last couple of years, have targeted at hybridisation of these technologies. So there may be some aspects and components that we can start to combine. For example, a conical component that has a cylindrical form. Similarly, also with additional features on the internal profiling. So things like that can be combined to, again, reduce the number of parts and have a much leaner process across the manufacturing route. So they're near net shape processes. We've got a huge amount of material utilisation as compared to conventional forging and machining, up to 80% improvement. It's also a volume constant process. So the volume of that preform going in is equivalent to the part that's coming out. And our processing times, I should mention, are very quick. So in terms of your conventional machining routes, we mentioned that earlier on in terms of the flow forming of shafts, and the amount of machining time to do the hollow bore on shaft components is significant compared to an up to 40-minute cycle on the flow former. Some of our smaller components or some of the conical parts, you're talking a 3-minute cycle time. So compared to your conventional processes, significantly improved. The mechanical properties can be significantly improved also, from fatigue to material hardness and grain refinement. It's something that we're particularly focused on at AFRC, is understanding the component integrity, but most importantly, how that may compare to a conventional method. Many of the projects that we work on, they're targeting cost reduction, but it seems to be that there's often a conflict of requirements between designers, between business, like the business case for those parts, in terms of reducing that cost, and it seems to need a compromise on quality. Now, with the near net shape processes, you do get that cost improvement, but also we can see an improvement in the quality of that part. So it's a win-win, but I think the key advantage of working with us is that we've been working with design teams to try and then embed design for manufacture of these processes that hasn't been embedded previously to get the most optimal outcome. High accuracy and control of these processes, and wall thicknesses where as fine a tolerance as 0.1 of a millimetre and 0.2 degrees in cone angle. So again, we're reducing the need for final machining, and surface roughness, as mentioned before, is typically equivalent to or better than machined methods. Energy costs can be significantly reduced, and overall the value stream can be much leaner. That's everything from me, thank you.
Thanks, May. I'll now pass you over to my colleague Jared Brown to discuss working with MNIS.
Thank you, David. Hello, everyone. As David touched on there, what we'll be discussing today is how to work directly with NMIS, building upon the technologies which were shown by Mark, Javad and May. So you can see here within the Forming and Incremental Technologies team, everything starts with an innovative project. The projects are at the heart of what we do, but within the projects, we also have several key aspects which we try to incorporate. The first of which is the skills development and learning. And Mark touched on this as part of his forging strategy, that we are a very people-oriented business. So we work with internal staff such as apprentices to develop the next generation talent. We work with future graduates through our summer internship programme. One of the projects which one of our summer interns currently done was forming an alloy wheel in line with our engineers. And that can actually be, the results can be seen on our LinkedIn page. We also engage in STEM activities such as primary engineer. And out with this, we also obviously engage industry when it comes to skills and development as well. I think Mark especially touched on that we are looking at training and consultancy offerings as well. As well as this, we've also got problem-solving capabilities. So whether that is a current manufacturing challenge which is facing your business, or indeed a challenge which you foresee coming in the near future, we can definitely have a look at that. One of the ways in which we can contribute to a business which doesn't immediately have a challenge facing it is that we can come to your business and walk the line, and look at your processes and come up with ideas in ways that we could either change your processes or improve them. The other one is obviously project support. So if you have long-term initiatives which you need support with, we can definitely arrange a structure which would support that to work together. As May touched on, we are the Forging Incremental Technologies team, but we are also supported within the wider NMIS group by digital technologies, residual stress and materials characterization, and machining as well. So we have a very broad approach. Next, we have bid development. So if you have a research idea which may be fairly low level, or you feel like would benefit from increased expertise either from academia or other consortium partners, then we can help you to generate a bid with your bid writing and take it to public bodies for funding. And of course, the overall goal for us is through each strand is to transfer knowledge from ourselves out into the supply chain and industry. So what I'm going to do now is touch on a number of different ways in which we can engage together through different types of projects that we can do. And as well as this, I've got a nice case study to support and illustrate this example. So first of all, we have the aptly named directly funded project, whereby NMIS and NMIS will engage directly with a customer, in this case it was Safran Landing Systems, to look at an existing manufacturing challenge. It's important to note that in this type of project, it's fully funded by the customer, and IP as a result is fully owned by the customer. This makes this type of project good if you've got a specific manufacturing challenge which is core to your business and you need to retain all the IP. Looking at the specific industrial problem within this context, the company, or Safran Landing Systems, had issues with cost, material waste and long lead times on some of their products. We looked at their products as a group and identified flowforming as a suitable technique to manufacture the products, which then led to us carrying out and facilitating experimental trials on site, as well as microstructural and mechanical testing to verify the products produced. The practical outcomes: we were able to achieve a part which was 3 times the starting length with the required strength, which was obviously validated through the aforementioned techniques. And we predicted 50% cost reduction, and mostly due to reduced material usage. It's important to highlight here as well that the benefit of being able to elongate the part as much as we did from the starting preform is that although there may be machining required on the preform, we were able to extract multiple parts from one single length or formed length. That stops you from taking 3 starting billets and having to core out each individual billet. So there is also potentially a good process time saving there as well. The next type of project which I'd like to touch on is the collaborative public funded projects. These are typically larger scale projects with funding from public bodies such as Innovate UK, EPSRC or Scottish Enterprise, to name a few. The ownership of IP in these projects is typically defined in what's known as a collaboration agreement for all the parties involved. With this specific project, we aim to identify an alternative manufacturing process for production of transmission shafts for the automotive sector. We performed a process down selection, which enabled us to identify radial forging as a suitable contender as the process. We then carried out materials characterization on both the raw material to understand what the starting condition was, and then post forging as well to understand the benefits of the process compared to the traditional machining routes. Throughout this process, or throughout the project as well, we also engaged the UK supply chain. And the practical outcomes for this particular project, we developed a reliable geometric model for radial forging, which we can now use for most of our radial forging research through the technologies that Javad has previously shown you. And we also fully developed project forgings, which were able to be going on to be tested and validated in their final use. The last one I'd like to touch on today is a Catapult project. So as one of the Catapult centres in the UK and the only one in Scotland, we are allocated funding for our own capability development with the view that we grow UK industry impact and de-risk innovation. So the IP, which is associated with these projects, is owned by the University of Strathclyde, but that doesn't mean to say that companies can't get involved. In this particular example, a company was able to supply centrifugally cast material to the AFRC, and as a result, were able to be the first to gain insight to the project outcomes and potentially use any project know-how. The research challenge, in particular, for this project was to determine the feasibility of using centrifugally cast materials as a basis for flow-forming preforms. The idea behind this was to reduce the material wastage from machining a preform, but also to get the benefits of centrifugal casting, such that you get a forged-like microstructure, and you're able to tailor the cast as well to suit specific properties if required. The techniques employed in this project from NMIS was we carried out some process and part design to identify a suitable experimental design, and we carried out similar testing as before, hardness testing, microstructural analysis on the parts, and obviously the flow forming trials themselves. Practical outcomes in this sense, where we were able to prove that the centrifugally casted material supplied to us by our industrial partner could be deformed up to 75% without any defects, which was a fantastic result. But it also did allow us to identify an area for future research, which is really key. The way we identified that was when we came to extract the samples, we noticed that there was an abnormally high residual stress within the components. So that's something that we can look at in the future, and that's something that will be supported by the wider groups at NMIS. So thank you for listening, and now we will move on to questions and answers.
Thanks, Jerry. Yeah, a great presentation there. I suppose we've had a couple of questions come in. One question someone's asked is our radial forge, what's the maximum hot forming temperature?
So, in theory, the maximum hot forming temperature will be limited by the material which you're going to forge. We have experience of forging up to and around 1200 degrees. Typically we're working in the region of 700 to 1000, but maximum I would say we've done so far is around about 1200 degrees Celsius.
I suppose one of the other questions we've had in as well is someone's asked how you would forge a yoke component. I'll let the folks answer that, but I suppose one of the answers would be depends the size and material used in that component and what it's going to be used for. But if anybody wants to pick that up in a bit more detail.
Sorry, David, can you say that again? What kind of component was that?
A yoke component for a four-wheeler.
Right, okay. As you mentioned, it does depend on like a lot of the various parameters, the kind of materials. We have experience with a lot of various materials, whether they come across from your aluminiums, your nickel alloys, your steels, etc., right across the board. In terms of capability at the FRC at the moment, if you're looking at the likes of our screw press, we have a die size between 180 and 290. So you put me on the spot for particular die sizes. And that's on our 2,100 ton screw press. So one of the biggest things that we promote in the FRC is the fact that if we don't have the capability at the FRC in terms of our equipment, we would work with you to either do the initial die designs and development, for example, and the modelling through the work that Java has presented. But we can then also work with the supply chain and help trying to find you a supplier who has a press capability to can either run validation trials or demonstration trials, but also then you can take that on for going forward with the likes of production discussions independently of the FRC following the kind of the introductions and that kind of work.
I suppose I'll mention a question I get asked quite a lot when I'm at events or even when people are in the centre visiting. And one question I do get asked a lot is how can we engage with the AFRC if we don't have a project at the moment? Thankfully, the AFRC and NMIS, it's a wonderful place to work and to engage with. Purely down to the fact is there's multiple ways to engage. It doesn't have to be on a project. We have webinars. Before COVID, we have people come in the centre to look around and discuss potential improvements. As Jerry touched on, we're happy to come to your site and have discussions about potential future plans you may have and improvements as well. And that doesn't just mean for the Forge and Incremental Technology teams. That means across NMIS as an organisation. Does anybody else want to touch on that as well?
Yeah, David, sorry, like we engage right across the sectors, for example, whether it be just from initial discussions and a bit of the kind of fault finding and see what we can do. Ultimately, we are here to help. But right across, as Jerry mentioned, like some of the kind of walk the line type discussions, right to like we'll do everything we can to try and help the supply chain through through either their problems or help them develop their ideas into funding or like funding bids, as Jenny mentioned, and opportunities going forward. It's not always just about problem solving. Quite a lot of the time it's about creating new opportunities as well.
I suppose as well, and I'll make this the last area to touch on it. It's something we get asked quite a lot within the team as well. Is how can we support you? And it is a two-way streak between ourselves. We need industry knowledge. We need to know what companies want to work on, what problems they're facing, so we can then work to answer those problems. And that comes hand in hand with industry engagement, discussions, idea sessions, even simple phone calls discussing what's going on in various different industries that use metal forming technologies. So if you feel you have some insight that might be useful for us, we are happy to discuss that as well. With that in mind, I suppose we'll move on from there. I'd like to thank everybody for their attendance today. If you have any questions, please email us at mnis-inquiries@strath.ac.uk and we'll get back to you as quickly as possible. And thank you for your time today, and we'll move on from there. You have a good day.
Thanks very much, David. Thank you for that. Hope everyone enjoyed today's webinar, and thanks very much to our presenters today. Shortly after this session closes, you will receive a survey. We would appreciate it if you could take a few minutes to complete this, as it does help us shape future events. We are having another NMIS Insights webinar on Wednesday, 23rd of September. The subject is Carbon Negative, Understanding Net Zero in Challenging Times. If you would like to register for this, you can find details on our website at nmis.scot. So I'm just going to close the event in a few moments, But again, as David said, if you'd like to contact us after this webinar, please email nmis-inquiries@strath.ac.uk. Thank you.